Williamson synthesis. This Williamson synthesis, it is useful for the preparation of ethers. Okay, so how can you prepare ethers by using Williamson synthesis? Now we can see. So in Williamson synthesis, we take alkyl halide. So here alkyl halide, generally we take RX. It can be reacted with sodium or potassium alkoxide. Okay, that means we take RONA or we take K. It is sodium or potassium alkoxide. So in this reaction, ROR, it is formed and byproduct is NaX. Okay, it is the preparation of ether from alkyl halide and sodium or potassium alkoxide. Okay, it is the best method for the preparation of ethers. Okay, right now we take an example. For alkyl halide, I take CH3CH2Br ethyl halide, and I take C2H5ONa sodium ethoxide. Okay, ethyl bromide, sodium ethoxide. In this reaction, the product formed is C2H5O, C2H5 plus NaBr. Okay, so here it is ethoxyethane. On both sides C2H5 group is present, that's why we write ethoxyethane. It is an ether. Okay, and here ether is see on both sides of oxygen same group is present, so it is called symmetrical ether. Okay, so now next we see another example. CH3 CH2Br plus CH3ONa sodium methoxide I taken here. So in this reaction, the product is CH3 CH2O CH3 plus NaBr. Okay, right now we see it is methoxyethane. Based on alphabetical order, we take the smallest group, we write oxy. So methoxyethane, it is also an ether. Okay, so it is Williamson synthesis. When you see these two examples, in these two examples it is symmetrical ether, because on both sides of oxygen ethyl group is present, so it is symmetrical. But it is unsymmetrical ethene. On left side 2 carbons, on right side 1 carbon only present. That means by using Williamson synthesis, we can prepare symmetrical ether as well as unsymmetrical ether. Okay, so you can prepare both sides types of ethers by using Williamson synthesis. Okay, so how this reaction takes place, now we can see from mechanism. So when you study about Williamson synthesis, you remember that Williamson synthesis, it is the substitution reaction, and here the substitution is takes place according to SN2 mechanism. That means it is a bimolecular nucleophilic substitution reaction. Okay, so if you write the mechanism, you see generally we take RX. Okay, it is alkyl halide. So here alkyl halide we take, right, and another one we take RONA. Okay, it is a sodium alkoxide. In these two, first you see RONA, it can be present as RO minus plus Na plus. It can be present like this. And next step, this RO minus, it can be reacted with RX. Okay, so RO minus, it is reacted with RX. It is a slow step. So in slow step means it is nothing but rate determining step. So here two reactants are involved in rate determining step. That's why molecularity can be taken as 2. At the same time, it can be present like this. R. Okay, see RO. Now it can be attacked to R, and in the side X can be eliminated. O minus X minus like this. An intermediate is present. At the same time, attack of RO group, leaving of X group is takes place. So here the compound formed is ROR, and here X group can be removed. This X group can be combined with Na plus. It can be formed as NaX. Okay. So this is mechanism for Williamson synthesis. In this reaction at slow step, two molecules can be involved. That's why it is bimolecular nucleophilic substitution reaction. In this reaction, in place of, okay, see, in place of halide, here the group substituted is alkoxide. Okay, X minus place. In place of X minus place, RO minus group can be substituted. So X minus, it is a nucleophile. RO minus also a nucleophile. So in place of a nucleophile, another nucleophile is substituted. That's why it is a nucleophilic substitution reaction. And its slow step, here 2 can be involved. That's why it is bimolecular nucleophilic substitution reaction. Okay, right. So here in this reaction, when you see alkyl halides and alkoxides are involved, so what is the reactivity order of alkyl halides? First we can see. Okay, so when you write reactivity order of alkyl halides, generally in this reaction, reactivity order is primary alkyl halide, it is more reactive than secondary, and least reactive is tertiary. Maximum cases should not consider tertiary alkyl halides. So primary, secondary, most reactive. Okay, within primary alkyl halide, okay, whenever you take primary alkyl halides, all are primary alkyl halides. In that which is more reactive, now we can see. Okay, all are primary alkyl halides. In that primary alkyl halides, which is more reactive? See, in that first we take CH3X methyl halide, and next C2H5X, C3H7X, C4H9X, like this. That means whenever number of carbon atoms are increases in primary alkyl halide, their reactivity can be decreases. So generally methyl halide is more reactive. Okay, and when you see reactivity order in this tertiary, if tertiary alkyl halide is present, that in that case ether is not formed. Okay, for example, here write an example. You see, if you want to prepare tertiary ether, okay, if you want to prepare tertiary ether, I take two conditions. You see, CH3, 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 ONA. It is sodium tertiary butoxide. Okay, now it react with CH3Br. It is alkyl halide. Here I take the alkyl halide primary. Okay, in this condition, primary alkyl halide I taken, tertiary alkoxide I taken. NaBr it is eliminated. The product formed is CH3, 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 OCH3 is present. That means it is nothing but tertiary ether is formed. Okay, right, same. I can change the positions. Okay, right, now I can take like this. You see, CH3, CH3, CH3. In place of ONA, now I take Br halide, and here I take CH3 ONA. Okay, in this condition, alkyl halide is tertiary alkyl halide. Okay, here I use tertiary alkyl only. I can change these two positions. In this example, primary, and here it is tertiary. So whenever tertiary alkyl halides we have to take in, instead of substitution, here elimination can be takes place. Okay, by eliminating that, here from CH3 it can be written like this, hydrogen, this bond can be shifted this side, here the bond can be broken, so it can be formed like this, CH3 C double bond CH2 CH3. That means the product is alkene. Elimination takes place. Hydrogen, it can be combined with CH3O, it can be formed as CH3OH, and here Br, it is combined with Na, it can be formed as NaBr. Okay, it is the product. So whenever you take tertiary alkyl halide, it is not substitution. Instead of substitution, here the reaction takes place is elimination. Okay, this is asking in examination, you can remember. Okay, so whenever you take, if you want to prepare tertiary ether, in that condition alkyl halide is primary alkyl halide. In Williamson synthesis, if you can use tertiary alkyl halide, instead of formation of ether, alkene formation is takes place, and here elimination can be takes place. It is dehydrohalogenation reaction can be takes place. Hydrogen and halogen both are removed. Dehydrohalogenation reaction can be takes place whenever that alkyl halide is tertiary alkyl halide. Okay, so you remember from this a question is asking in examination. In Williamson synthesis, it is for the preparation of ether alkyl halide. It is reacted with alkoxide, we get ether. It is belongs to SN2, bimolecular nucleophilic substitution reaction. But if you want to prepare tertiary ether, in that condition alkyl halide we take primary or secondary we have to take in. Okay, whenever you take tertiary alkyl halide, in that condition the product is alkene. Okay, this point you have to remember. Okay, in this reaction, if you can use tertiary alkyl halide instead of ether, alkene is formed. Okay, it is about Williamson synthesis.